So in this diagram, this part of the question, we see a picture which looks similar, but we notice a couple differences. Block W and block Z, when in previously we had blocks X and Y. And so that's an intentional attempt to make us realize that although the setup is the same, the blocks themselves are different. But what we do have in common is we have this release height, like so, and we have a delta Z, which is also called Hx. They're calling it Hx. And we have gravitational potential energy, which is mg Hx, which becomes kinetic energy, which is 1/2 mv squared. And we see the block then colliding. So in this part, the first part, we have the law of conservation of energy operating. And then there's a collision. And we see that when they hit down below, in this area, we have our conservation of momentum, which is going to govern it. But it looks like block W has a velocity of 0 and block Z goes off. And so now we look at the data that's provided, the actual speed of block W after collision. And what we look at is we seem to have 4 trials. And when we look at those 4 trials, we see that the sum of them is 0. So if we're going to average them, they average out to 0. So the average velocity is 0. And that's what we thought. We said it looks 0, and experimentally it turns out to be 0. And then we can look at the actual speed of Z. So that goes with block Z after the collision. And we notice there are these two, 1.3, 1.6, and then 2.1 and 2.5. So it seems like there's a natural bifurcation here in the data list. That like the first two seem to be like the same thing and the second thing not. To help see a little better what's going on, if we have like a 1.3 and a 1.6, if we were to average those would be about 1.45. And if we average the second two, those would be about 2.3. And we can see that's a very big difference. You know, we might say they're, quote, close together, but they're actually not. There's like a 60% difference between those. They're very different from each other in terms of their scale. And so that's the speed after the collision. It's the actual. And then we look at what was predicted to occur. So we look at the data, about 1.6 and 2.0. We get a mean of those about 1.8, and we see that same bifurcation of the first two and the second two. 2.4 and 2.7 is an average of about 2.5. So in both cases, we see the first two being smaller, both the actual and the predicted, and the second half, both of them being larger. But interestingly enough, if we notice the predicted is 1.8 and 2.5, and the actual is 1.4 and 2.3, so we could say overall is the actual is less than predicted. So there's a collision going on, and what we measure actually is less than what we predict. And so that looks like maybe there is some, it's not going fast enough, which means there is less kinetic energy than expected. Oh, so this thing is probably inelastic. Yet when we look at the collision, it is a bouncy collision, and we might expect for it to be elastic. But it's clearly showing that there's a loss of kinetic energy. Now, of course, that's if our assumption of following the picture is right. So let's go on and look at the question to give a little context to what we figured out. They repeat experiments with X and Y replaced with block W and Z. So we figured that out in the beginning. W and Z are not X and Y. W and Z have identical mass, which we were not told before. When the experiment is conducted, students observe the blocks do not stick together, as shown in figure 4. The students predict the speed of Z after the collision by assuming the collision is perfectly elastic. Well, what we can see is it's not elastic, so the assumption is false right off the bat. We can see that right off the bat. Assumption is false. All right, so the predicted then would give us the case if all the kinetic energy and were conserved, and in the second case there's kinetic energy. What actually happens is the kinetic energy is not conserved, so their assumption is false. Then they collect data about the actual speeds of both blocks immediately and shown in the table. Why does the predicted speed of z after the collision not agree with the actual speed of z after the collision? So the first thing we notice is that the assumption is false. And the second thing we might notice is why might that be the case? All right, so we know that all of this energy that gets lost has to do with that time when the particles are interacting with each other. And what are the things that can happen? Well, kinetic energy can be transformed into thermal, sound, and vibrational energy. So these are the two statements. We're looking to explain this here a little bit more detail. And so, so the first thing we would say is that the assumption of elasticity is false. The EK is not conserved and is less than predicted, indicating that some kinetic energy is transformed into other non-mechanical forms of energy, such as thermal, sound, and vibrational. The loss of EK during the interaction means less EK afterward, and therefore a lesser velocity. So that's our attempt at answering this question. Now we'll go and check the scoring guide. Indicating the collision is not perfectly elastic. Good, so we said that. Assumption elasticity is false. It's not conserved unless I'm predicting any that's something. Good, so we've got that. Indicating a conceptually appropriate reason why the collision is not perfectly elastic. So we look at their sample answer is not perfectly elastic, even though the two blocks do not remain stuck together. Okay. During the collision, the two blocks may have momentarily stuck together, or the block may have slightly caused a temporary deformation to occur with the surface of the other block. So I don't find this answer actually adequate, because temporary deformation is not energy. So deformation itself, work is done. So you have a fixed object like this, and there is a force applied on that, and that force does work on the blocks, which creates internal friction, resulting in thermal energy, or as you're used to seeing it in chemistry, a delta Q. It's a change in delta Q. Okay, so I would expect this to be explained in terms of energy, and deformation is not energy. If we're going to say deformation, we want to also explain that during the process of deformation, that takes work, and that work is manifest as thermal energy. Okay? The other part of this that's a little bit different than our answer is this: even though the two blocks do not stick together. Okay? In other words, even though it's bouncy. Now, it's not absolutely necessary for us to include it, but we might as well. We've noticed it here. We noticed it, we used it in our thinking. You know, see, this is false. And that's where we could have added something like, even though the particles don't stick together, they actually bounce off each other, EK is lost during the interaction. All right, and I would just want to point something out that is that the idea of elastic and inelastic is what I would call a false dichotomy. Now, a dichotomy is something that breaks things down into two categories. Seemingly opposites or exclusionary. And so we could say that something is completely elastic. That means 100% of the kinetic energy is conserved. The flip side of that might be to say it's inelastic, in which 0% of the kinetic energy is conserved, which is hard to imagine what that would be, but everywhere in between there is a gray area. And so if we take a ratio of the elastic, the initial kinetic energy to the final kinetic energy, I should do that backwards. Let me flip that. If we do the final kinetic energy to the initial kinetic energy, well, if it's 100%, those two will be the same, and that will equal 1. But let's suppose we have 500 joules afterward, but we started out with 1,000 joules. Then we could see that that is 50%. And so this ratio of the final to the initial gives the elasticity. It's a measure of how elastic it is, of how elastic the interaction is. And so, the truth be told, that no interactions, none, are perfectly elastic. There is always going to be some loss. The question is how small, how little will be lost. You know, if we think of things like marbles or billiard balls, these types of things, that's the case. And we saw this before when we had a ball that was interacting with a surface and compressing, that the marbles or the billiard balls, the delta T is small. So there's little time for there to be work done on the object and energy to be transferred. So as the delta T decreases, the more elastic it becomes. And so the real answer to a question is how elastic is it? Is it 99% elastic? Is it 98%? Is it 100%? Well, 100% is ideal. It's like no air resistance. Really? Well, there's always air, right? So we can neglect air resistance, and so that's what this is like. And, you know, it may come down to that when we have the kinetic energy final, there's a plus or minus, and the initial kinetic energy, there's a plus or minus. And those two overlap so much that you can't tell them apart, in which case you have 100%. All right, so that's something to be aware of in this case, taking this a little bit further than where the AP wants us to be with it, so that you have a more full understanding.